Hello, and welcome to this lecture on Unit 2, Homework 1 of Application of Derivatives. My name is Paul Nussbaum, and I'll be leading this lecture today. First, I want to give you an overview of what we're going to read before doing this homework. For this homework, you really should review Chapter 24 on your own. Not all the problems in the homework are going to be clear just by looking at this lecture by itself. This lecture is really meant to give you an overview of the reading, but really you're expected to use the textbook for your primary source of information. So Chapter 24 covers these areas. We'll be going over them in detail, but I included this slide in case you wanted to review it on your own. So the homework spends time pretty evenly across all the sections of the chapter. The reason why we're doing that is that it's very important that you learn these applications of derivatives. You'll be using them in your engineering technology careers when it comes to finding the rate of change of something that's moving, the rate of change of a voltage that's varying over time, and then also the acceleration of those things. The following slide really breaks down the homework for you so you know what you're about to get into when you jump into the homework number 1 in Unit 2. Some students will use this next slide and keep the book open as they do the homework problems. So as you can see, the homework problems are numbered 1 through 27 on this page here. And you can see not only the question ID, but really it shows you which chapter and section. So the first question is Chapter 24, Section 1. That other number after the 1, that .5 on the first question, that's not really meaningful to you as a student. It has to do with what number of that question out of the question pool if we were to randomly select questions. But that's not really important to you as a student. Really just the first two numbers. 24.1 means that it's Chapter 24, Section 1. So sometimes students use this page to kind of give them a gauge of where in the book to find help on a particular problem. And sometimes the problems themselves have a click button to go ahead and bring you to that page of the book, but they don't always, so that's why I'm including this sheet here. So the focus areas of the homework are these sections, and I'd like to go through them one by one at least so you understand what you're going to be coming up against when you do the homework problems. So let's go section by section and take a look at an example in the textbook from those focus areas. First, let's start with tangents and normals. So we're trying to understand the meaning of the word tangent. A tangent is a line that just barely touches a curve at one spot only, at one point only. So, for example, let's say we have the curve y equals x squared minus 1, which might look just like this graph right here. And if we want to find the tangent of that at a particular point, let's say -2, you can see there's a dot drawn at the -2 spot. If I plug in -2 for x, -2 squared is 4, minus 1 is a 3, so y equals 3. So the point shown on the graph is -2, 3. So that's the point on the graph. Now I'd like to draw the tangent to that curve at that point and actually write the formula for the line of that tangent. So how do we go about doing that? Well, first we take the derivative of the original function. So y equals x squared minus 1. Take the derivative of that, and that's 2x. So that gives us the formula for the slope of any line touching that curve. Basically, the tangent of the slope of the tangent of any at any given point. Then I'll go ahead and plug in the point that I'm looking for. I'll plug in a -2. So I'll evaluate the derivative at -2. And I see that 2 times -2 is a -4. So the slope of the curve at the point -2 is a -4. It's going downhill, and you can see that from the picture. So here they're using a kind of a cutesy way of determining the formula. Really, all you need is the slope. because once you know the slope, you can plug in x and y to find that constant. But here they're using a cutesy way of finding the point slope form of a straight line. So they'll say, look, if I subtract 3 from y and I add 2 to x, basically both sides will become 0 because those are both points on this line. Because I know that one of the points on the line is -2, 3. That's basically what was asked of me in the very beginning of the problem. Find the formula for the tangent line at point -2, 3. So what they did is they just subtracted that point from both sides of the equation. So they knew that the equation was y equals -4x plus some constant. And they used this cutesy way of finding it by subtracting that point from both sides. You could have just gone to that last equation on the page, y equals -4x minus or plus some constant, and then plugged in values of one point that you knew, -2 and 3. But so there's a couple of different ways to find the equation of the tangent line once you know the slope and one of the points on that line. So use whichever way you're comfortable from algebra class, but really the main thing is we have to find the slope and we have to know at least one point on the line, and from there we can find the formula for the tangent. Now if you want to find the tangent line of an implicit function, we might have a function where it's not so easy to pull the y on one side of the equal sign and everything else on the other side. So let's take, for example, this ellipse. An ellipse can be described by the equation 4x squared plus 9y squared equals 40. And we'd like to find the formula for the tangent line at point 1, 2. So first I want to find the slope. Then I want to use the point and the slope to find the formula for the tangent. So to find the slope, first I have to find the derivative. Now remember, when you have an implicit function, whenever I take the derivative of something that's got an x in it, I use the old-fashioned way of using the techniques we know. So the derivative of 4x squared is 8x. But when I find the derivative of a y value, I'll need to add the y prime to it. So the derivative of 9y squared is 18y times y prime. Then I just move everything around, so y prime is the only thing on one side of the equation. That gives me y prime equals -4x over 9y, and you can prove that to yourself by doing the algebra. And then I'll evaluate y prime at that point that we know it's going to be at, 1, 2. In this case, I need both numbers, both the 1 and the 2, because I've got both x and y on that other side of the equation. So I plug in a 1 for x and a 2 for y, and I end up with the y prime is a -2/9. So the slope of the tangent is -2/9. Now here, once again, they're using that point slope form of the tangent line, but really you just need to use any form that you want. Once you know the slope of a straight line and one of the points on that straight line, you should be able to come up with the formula for the line. But in either case, we have a parametric form of that line. 2x plus 9y minus 20 is equal to 0. So it's a way of writing that kind of an implicit function. Now when we're finding a normal line, we have to remember that the slope of a normal, or a line perpendicular to another line, has the slope of negative the reciprocal. So first we have to understand the problem. It's got a formula, y equals 2 divided by x, and we need to find the normal at some point 2, 1. So here's the graph. Those curved lines show the hyperbola, y equals 2 divided by x, and that diagonal line on top of it shows the normal to that hyperbola. In other words, at that particular point, 2, 1, that is the line that is not tangent, but it is perpendicular to the curve. So that's really what we're looking for. So once again, just like for tangents, we take the first derivative, and remember, since y equals 2 divided by x, that's really the same thing as saying y equals 2 times x to the -1 power. So that makes finding its derivative easy. The derivative is negative 2 over x squared, really negative 2 times x to the negative 2 power, if that makes it easier for you to solve the derivative. And then we'll evaluate that derivative when x equals 2, because that's the point that we're looking for this intersecting line. And the slope there is negative 1/2. We need to take negative the reciprocal of that, so the negative reciprocal of minus 1/2 is a positive 2. So the slope of that normal line is positive 2. Once again, I plug in the values for x and y that I know to go ahead and get the formula for the line. Here they're using that point slope technique again. And they find that y equals 2x minus 3. Once again, you knew that in the slope-intercept form, y was going to equal the slope times x plus some constant, and you can figure out that constant by plugging in the point parameters that you know, but they've done it this other way. That's fine. So Newton's method for solving equations is a clever way of solving some pretty tricky problems. And the problems that we're trying to solve is to find the roots of an equation. Now you remember using the quadratic formula. You remember trying to find roots of equations when you were trying to go ahead and factor out a polynomial. Those were all pretty tricky, and the more complicated the polynomial got, the trickier finding the roots was. And Newton realized that, so he wanted a surefire way to find the roots of any equation when it's really difficult to factor or use the quadratic equation. So the trick that he used was he made some sort of a reasonable first guess, and then he used that first guess to get a little bit better approximation, and he kept doing that until he got close enough that was suitable for his needs. In engineering, we usually want to get close enough so that anything different from that value that we've gotten is not significant to the problem we're trying to solve. Usually that's, for example, in a computer. If we get so accurate that it's more digits than, let's say, a 64-bit computer can hold, there's no point in solving it more accurately than that, because we can't even store the answer on the computer more accurately than 64 bits. So those are kind of why we use Newton's method quite a bit, especially for tricky problems. So Newton's method basically takes a guess, let's say x1, and then calculates a slightly better guess, x2, by using this formula. x1 minus that original function evaluated at x1 divided by the slope of that function evaluated at x1, that derivative. So that's kind of getting closer and closer to a better value. That's Newton's method. Let's go ahead and use it on an example problem. We want to find the root of x squared minus 3x plus 1 equals 0. So we want to go ahead and find what value of x will make that equation equal 0. And they're giving us a hint. They're saying that the answer is somewhere between a 0 and a 1. So here we see that the value of f evaluated at x equals 0 is a 1. So I plug in x equals 0 and I get the answer 1. If I also plug in x equals 1 and evaluate the function, it comes out to be minus 1. So if it's a plus 1 on one side and a minus 1 on the other, maybe the root, basically where it equals 0, might be somewhere in the middle. So my first guess, I'm going to say, is 0.5. So to use Newton's method, I need to know the derivative of the function. So I've got x squared minus 3x plus 1. Take the derivative. That's derivative of x squared is 2x. The derivative of minus 3x is 3. And the derivative of plus 1 is nothing, 0. So the derivative is 2x minus 3. And then I'll use that Newton's method function. My second guess is going to be my original guess minus some increment. F of x evaluated at x equals 0.5, and f prime of x evaluated at x equals 0.5. So I plug in 0.5 into my equation, and I get negative 2.5. I'm sorry, negative 0.25. And then I plug in 0.5 into my derivative, and I get negative 2. Solving the problem, I find that my next guess would be, a better guess would be 0.375. I can keep repeating this, getting closer and closer to the answer until I'm as close as I care to be. And that's pretty much Newton's method. Curvilinear motion really means that it's curvy, but it's on some sort of a flat plane. So, for example, the path of a cannonball is exactly curvilinear motion. You can imagine cannonball goes up and then down. It's kind of a curved motion, and but it always travels along a flat plane that it's moving through the air. So a lot of times these curvilinear motion problems are parametric. In other words, it's not y equals some function of x. It's really both x and y are functions of a third variable, a parameter. In this case, it's time. So if I could say that this the horizontal distance that the cannonball moves is given by some function x equals 3t squared. And the vertical distance, the height of the cannonball, is more dependent not on how much gunpowder I put in the cannon, but more on which angle I pointed the cannon. So the vertical distance, y, is given by another function, 1 minus t squared. So that could be something that kind of goes up and then falls back down again. So I want to find the resultant velocity at 2 seconds into the flight of the cannonball. So I'll use this parametric form here. Both x and y are evaluated in terms of time, t. And we're going to solve this curvilinear motion problem because I know velocity is the first derivative of distance. So I know x and y in terms of distance. I want to find the velocity, which would be the rate of change of distance, right? So here's that function, and there's that cannonball being fired down from some point. And I know that the total velocity is equal to a function of both the x velocity and the y velocity. So the velocity, total velocity, is a vector. It has both magnitude and direction. So what I'm going to have to do is I'm going to have to find the derivative with respect to a derivative of x with respect to t, also the derivative of y with respect to t, solve them for both at the value time equals 2, and then I will convert that vector from rectangular to polar form. So let's go step by step. The first row shows that the velocity in the x direction is the derivative with respect to x. So I've got x equals 3t squared, so its derivative is 6t. Then I evaluate that at time equals 2, plugging the 2 seconds into the 6t, and I get it that the velocity in the x direction is 12. The second row says the velocity of y is the first derivative with respect to time of y, and y equals 1 minus t squared, so the derivative is negative 2t. Plug in 2 seconds into that, and I see that y is kind of going in a downhill direction. The velocity is moving south at negative 4 units per second. So I evaluate that at time equals 2. That's where I got the negative 4. So that kind of gives me a rectangular format. It's got a velocity of 12 in the x direction and a velocity of negative 4 in the y direction. You can see that on the graph. If I want to convert that to polar form, I need to have a magnitude and a direction. So a magnitude, I've just used Pythagorean theorem to see how long that diagonal v is. So the 12 squared plus minus 4 squared, all take the square root. I come up with a 12.6. And that answer makes sense to me, a little bit longer than 12. And then to find the angle, or the direction that it's moving, I would take the tangent, or the arctangent of negative 4 over 12, because I know the tangent of theta will be 4 over 12, so I take the reverse tangent. Some calculators say arctangent, other calculators have a button that says tangent to the minus 1 power. They both mean the reverse of tangent. So I plug that into my calculator. I know that it's pointing in negative 18.4 degrees. So that's pretty much how we would solve a parametric curvilinear motion. We can do it also with the second derivative. So let's take a look at the second derivative. If I take the first derivative of some sort of motion, it means I'm finding the velocity. If I take the second derivative of some sort of motion, it means I'm finding the acceleration. Velocity is the rate of change of distance over time. How many miles per hour? The change of distance over time, miles per hour. Acceleration is the rate of change of velocity over time. So I'm accelerating at 2 meters per second squared. Let's take a look at it in a formula. I want to find the magnitude and direction of acceleration at time equals 2 seconds for some object that's moving through space such that its x-coordinate is t cubed and the y-coordinate is 1 minus t squared. So I know that because I want acceleration, I'm going to have to take the derivative twice, or take the second derivative. So here's that that curve once again, and I want to find the acceleration now at that point in time. So first I take the first derivative with respect to x, and I see it's 3t squared, right? Because the derivative of t cubed is 3t squared. So that's the velocity. The velocity is the first derivative. The velocity in the x direction is the first derivative. If I want to find the acceleration of in the x direction, I had to take the derivative of the derivative, something we call that a second derivative. So the derivative of 3t squared is 6t. So the acceleration in the x direction is plug in t equals 2 seconds into 6t, I get 12. 12, let's say it's meters per second squared in the x direction. Then I repeat it in the second row in the y direction. The first derivative is negative 2t. The second derivative is a plain old negative 2. So no matter what time it is, the acceleration evaluated at time equals 2 seconds is always going to be a negative 2. So once again, I have that in rectangular format. It's accelerating 12 meters per second squared in the x direction and negative 2 meters per second squared in the y direction. If I want to convert that into polar form, I need to know magnitude and direction. So once again, I use Pythagorean's theorem, 12 squared plus a minus 2 squared, and then take the square root of that, so I get 12.2, and then you see that in the graph, those arrows adding up with vector math. And then I take the reverse tangent of minus 2 over 12, and that's how I get the minus 9.5 degrees. So this is how fast that cannonball is accelerating in the at that point time equals 2. So related rates help us determine the rate of change with regard to a different variable than is originally provided in the function. Let's take a look at an example. So the voltage E, now don't confuse V with E. E is used in Europe and other places as well. It's called electromotive force. So instead of the capital letter V, they use the capital letter E. So the voltage E of some thermocouple is a function of the temperature. And that's measured in Celsius, and it goes with the variable T. And that formula is the voltage, E, equals 2.8 times whatever the temperature is, plus 0.006 times the temperature squared. Now let's say I've attached this thermocouple to some sort of a water heater, and that water heater has a temperature that's increasing at the rate of 1 degree Celsius per minute. I want to know how fast is the voltage increasing when the temperature is at 100 degrees Celsius. So because we're asked to find the rate of change of voltage over time, I have to take the derivative over time. So that gives us this formula. I want to know the rate of change of the voltage over time, which is equal to the rate of change of the temperature over time, plugged into the formula that we use for voltage. So we said that the voltage is equal to 2.8 times the temperature plus 0.006 times the temperature squared. I'll go ahead and take the derivative with respect to the rate of change of temperature over time. That gives me 2.8 rate of change of temperature over time, plus 0.012 times the temperature times the rate of change of temperature over time. So basically I took the derivative of temperature over time, but I left in the dt d temperature d time next to each one. Why? Because later on I already knew that what was the rate of change of temperature over time. It was given in the formula in the original question. It said that the rate of change of temperature over time was 1 degree Celsius per minute. So I'll just plug in that 1 degree Celsius per minute into my original formula, just as I'll also plug in the temperature of 100 degrees Celsius. And that's how I can tell that the voltage is going to be changing at 4 volts per minute after I plug in those. So those are related rates. That's when one thing is changing with respect to another. And there's a number of those examples in section 24.4 of chapter 24. The other thing that chapter 24 talks about is using derivatives to go ahead and sketch a curve. So we might have some complicated function, y equals x cubed minus 3x, and we would like to know some sort of a linear approximation of what the heck that looks like on a graph. So we use some terms that help us sketch a curve, and I just want to go over them really quickly. This is from the study sheet of the same chapter 24. Concave up, meaning concave, meaning like a cup or a cave. Basically, it's shaped like a cup, but the cup is pointing up. So the blue part of this curve is concave up. And if something is concave up, there must be a relative minimum. It means if I put a marble in that cup, where would it eventually stop rolling? What's the bottom of that cup? So that's the relative minimum. That's the blue dot that you see here on the curve. So concave up means it's a cup pointing upwards, and relative minimum means it's the bottom of that cup. Opposite is a concave down, so it's the red part of the curve. You just turn the cup upside down. And relative maximum means the very top of the mountain, basically the opposite of what you saw in the blue. Now it's the red dot that's the very top of that mountain, right? So we can go ahead and find these values using the original formula, y equals x cubed minus 3x. We see that the first derivative, y prime, is going to be equal to 3x squared minus 3. So that's just taking the derivative of the original equation. And you can see that there's where does that y prime, 3x squared minus 3, where does that become 0? Because y prime, isn't that the slope of the curve? So in that mountain part of the curve, the red part, you can see that on one side of the maximum, it's going uphill, and on the other side of the maximum, it's going downhill. So at the very top of the mountain is the only spot where the derivative will be equal to 0. It's neither going uphill nor down, it's kind of flat. So where does that equal 0? You can see that the curve equals 0 at the very top of the mountain, the relative maximum, the red dot, and also at the very bottom of the cup, that concave down, that relative minimum, the blue dot. Both at x equals minus 1 and x equals 1, that's where the first derivative equals 0. And you can plug in x equals minus 1 and x equals plus 1. They both make y prime, or the first derivative, equal to 0. So I've used the first derivative to find the relative maximums and relative minimums. But how can I tell if something is concave up or concave down? Because that will tell me whether that relative is a maximum or a minimum, won't it? Well, if I take the second derivative, y double prime, and that's equal to 6x, then I know that the second derivative is the rate of change of the slopes. So you can see in the red part of the curve, the slope is always getting smaller, even when it's going uphill and then finally flat and then downhill. So always the slope is getting smaller and smaller and smaller, and more negative. But on the blue part of the curve, you can see that the slope is always getting bigger and bigger. It is negative to begin with, but it's getting less and less negative until finally it's a zero, and then starts going uphill, and it goes steeper and steeper. So the second derivative really tells us if something is concave up, meaning it has a positive second derivative, or concave down, it has a negative second derivative. Also, when the second derivative is exactly zero, neither positive or negative, that tells us where the concave up meets the concave down, where the red line meets the blue line. We call that the point of inflection, where things were going like a mountain, and then suddenly they're turning into a valley. So these three formulas, the original formula, the first derivative, and the second derivative, help you go ahead and sketch any kind of a curve. So we can go ahead and use this relative maximum and relative minimum in an engineering problem, not just to sketch curves. And that's really what section 7 of chapter 24 talks about. So let's use this in an example so you can see how it works. We've got some automobile manufacturer, and they're testing their new engine, and they found that the efficiency, in percentage of efficiency, is really a function of how fast the car is going. So the efficiency equals 0.768 minus 0.00004 s cubed, where s is the speed of the car in kilometers per hour. So what is the maximum efficiency of the engine? You can see that if the engine has this efficiency here, then I'm looking for a mountain, and I'm looking for the peak of the mountain. So I want to know where the efficiency is at the very top of that mountain. Because what I'll find is that the efficiency goes up as the speed goes up, but then it starts to drop as the speed gets even higher. So what do I need to find the peak of the mountain? I have to find the first derivative and set it equal to 0. So the first derivative is, with respect to time, is 0.768 minus 0.0001, 12 seconds squared. So that's pretty much how we're going ahead and taking that first derivative. And I'll go ahead and plug in values that make it equal to 0. And I'm thinking they're missing an s in this equation. E equals 0.768 s minus 0.00004 s cubed. So I think they're missing an s in their equation. Sorry about that. But basically, they set the derivative equal to 0. And then I can solve for what value in terms of how many seconds pass will that formula equal to 0. It's just I have to take the square root of 64,000. Now, 64,000 has both a positive and a negative square root. The speed could be 80 kilometers per hour, or it could actually be negative 80 kilometers per hour. They both, when you square them, equal 64,000. But we know that s has to be positive. It doesn't matter. No point in me telling you to drive the car in reverse. So the speed of the car is 80 kilometers per hour. And what I'll find the efficiency in that, here they've correctly re-added the s to the equation. So 0.768 times s, which is 80 kilometers per hour, minus 0.00004 times 80 kilometers per hour cubed. That gives us 40.96, basically 41% efficiency at 80 kilometers per hour. So here you can find the local maximum, helps you go ahead and basically solve an engineering problem. So with regard to differentials and linear approximations, we always did dy dx. It's kind of like a fraction, right? dy divided by dx equals f prime of x. But if you multiply both sides by dx, you see that dy equals f prime of x times dx. So that we call those, when we separate dy from dx instead of always using them as a fraction, we call those differentials. So not to confuse you further, but let's take a look at an example. It'll be easier to understand when we're looking at an example. So here, instead of x and y, we're using s and t. So s is a function of t. S equals 4t divided by t squared plus 4. So to do the differential of s with respect to t, I would have to use the quotient rule, the top part being, let's say, a u, and the bottom part being a v. So remember that the quotient rule says v times du minus u times dv divided by v squared, right? So here I've got t squared plus 4 times the derivative of 4t, which is 4, minus 4t times the derivative of t squared plus 4 is 2t. All of that divided by t squared plus 4 squared. So that's the derivative quotient rule. But notice here, instead of saying ds dt, I've put the ds on one side and left the dt on the other. Because after all, it is a fraction. I just essentially multiply both sides by dt. So doing some algebra at the top, I go ahead and group like values. I'm leaving the denominator the same because it's kind of a pain. But basically, now that I've grouped values together, I find that ds is equal to minus 4t squared plus 16 divided by t squared plus 4 squared. So remember that if we just say ds on one side, I have to write the dt on the other. We call those differentials instead of the derivative because now I've separated out that top and bottom half of the fraction. So let's talk about how you'll be assessed. Let's say you finish the homework and the other assignments in Unit 2. You'll have a quiz covering all of Unit 2, and most of the questions from that quiz are going to come from this chapter that we just went over, Chapter 24. So about 12 of the 18 questions in the quiz are going to come from this chapter. This way you know kind of what's coming on the quiz. Also, there'll be a final exam at the end of the term, and it's going to have 2 or 3 questions from this chapter. It's not really, final exam is not focused on this chapter. Instead, it's really things that you learn in this chapter are going to be needed for future chapters. So that's kind of where we're going with the final exam. The study sheet that's also included with this lecture is basically focused on the definition of some key words that you come across in the chapter. If you don't understand what the meaning of these words, like if you don't know what a tangent line is, it's going to be very difficult to solve any of the problems in the homework. So in order to understand Chapter 24, you need to understand the words. So that's what the study sheet is about. It goes ahead and shows you the portions in the chapter, and they're pretty much in the order that they appear in the chapter. So thank you so much for listening to this lecture. Basically, it's a homework overview of that first homework in Unit 2. It's based on the textbook Basic Technical Mathematics with Calculus by Alan J. Washington from Pearson Publishing, and all of the formulas and diagrams in this lecture were taken from that textbook. So thank you so much for listening, and have a great day.